Arch Logix 5000, which is the newest version of Allen Bradley's PLC programming application. And this is a language called sequential function chart. Oh, apparently. This is not really the one I was looking for. Hopefully I can find the other one in here. So this is a language called sequence function chart, which is basically what we're doing. This is really rudimental because I was just trying to, still not turned on. Directly from a sequence function chart. So you have a step that you wanted to do something, then you put what's required to transition to the next step. See that? So this is exactly what we're doing over here. But you could take these sequential function charts that we're looking at now, and we could use this to program a PLC that recognizes this language. So this guy, Arch Logix 5000, we can do function chart, sequential function chart. We can do function charts, function block, which is basically digital. So this is function block programming. So these are hands, dead hands. So that's dead hands. Then we have holders. So if you take digital, I don't know if y'all are required to take digital. I don't think y'all are, but that's in digital. What we have is we have a bunch of symbols that represents the different logic functions. These are the ISO, the International Standard symbols, which is basically blocks. So Boolean AND, so it says for this output right here to go true, then this sensor right here has to be true, this sensor has to be true, and the start button has to be locked. It's correct. Then it would fall into there, right? Now this is what we call a set reset latch. So that would set it, that would cause this output to be true. How would we reset it? Well, if 2P1, which is the pressure switch, if it goes true, or the reset button on the front is pressed, then that would reset that. So this is basically the operation, I think, of the first module on the Festo line. But this is called function block programming. Then, of course, the main language that just about everybody uses, which is the industry standard. It's the most widely used. Something called ladder. You can figure this out strictly from DC. So the way ladder works is this is one of your power rails. This is your other power rails. And then we build circuits between the two power rails, right? You understand? So this is nothing but a circuit right here. These represent contacts. You know what contacts are? They open and close. So we would come over here back in DC. So back in DC, you had a trainer, right? And you could turn your trainer off and on, right? So let's look at this light circuit over here. So I come over here and I've got a switch, and then we've got a light up there, and then that would be a complete circuit. Now, the way these things work is basically somehow we're just taking two conductors. We're just taking two conductors and bringing them together. This right here is what we call, this right here would be what, it's got the name as a contact because it's the contact point between the two conductors. Well, what we do on a relay, so a relay is we'll have an electromagnet. Then we'll have some type of armature. So this would be a piece of metal. And we'll just do it this way. So this is going to be a very simple relay. Some are more efficient than the others. And then we'll put a spring right here. And then we'll put another then we'll put that right there. And then when we come over here and energize our electromagnet, it pulls this thing down and closes the contact. Well, in relay logic, what we would do is we might come over here and do this. So the symbol we use to represent this coil of wire, so this is nothing but a coil of wire. The symbol that we use in electricity and electronics and just about any trade you go into, you're going to have symbols, right? You understand? And symbols are used to represent things. And now we put symbols into our drawing. Instead of trying to draw the relay, we have a symbol that represents the relay. Well, what we would do is we'd come over here and we'd put a little circle, and we don't put dashed lines coming out of the top of it. And this is the symbol for the coil. So when I come over here and close that would energize the electrical magnet. So that's the actual symbol of the electromagnet itself. We refer to that as a coil, right? And it's going to close a set of contacts. Well, what we would do is we would come up here and we would give the relay a name, like CR1. And then I would come down here in the next line and I would come over here and I would do that. So this is a contact. It's what we call a normally open contact. And I might come over here and put a light bulb over here. So what it means, I come over and closes this, it would energize the coil, but I'd have to give, I'm sorry, I forgot something. I would give this the same name as the coil that's controlling the contact, right? Does this make sense? So I come up here, I close that, it would put power across our electromagnet, it would pull the armature down, it would close this contact, and the light would come on. And this would be basically, but this is, we call this is called ladder logic, or ladder diagram. Why? Because it looks like a what? It looks like a ladder. And each one of these individual circuits, we call this a rung. And what's nice about relays is that, well, let's so this is a symbol from what we call, this is a symbol for a momentary contact push button. Y'all understand what that term means? So momentary contact means it's only made when I do what? Push it down. Well, then we've got this guy right here. So this would be a normally open. So that means the circuit is not made until I press it. And then we can come over here. And we'll draw this under the bottom, and we'll do the same thing. Well, this would be a normally closed momentary contact push button. Make sense? Okay. So in industry, you see a lot of push buttons. You don't see many switches because push buttons are easy to operate, right? You understand that, and they're easy to operate with gloves on. These little switches that we run into that you see, that understand they would be what? Harder to operate, and you got to figure out what's going on. So what we would do with this one, this is a pretty standard circuit right here. This basically is a memory circuit. So right now I come over here and I press the button, energize the CR. It's a momentary contact, but when it comes up here and energizes it, what does it do? It closes that contact right there. And the light comes on, which is going to close this contact right here, and the light's on. And it seals itself in, right? So now we bypass the start button, and now how do I stop this thing? Well, I come up here and press that button, it would open up the circuit. So y'all see this all the time. So you go up there and you see a start button, you press it and release it, and the motor keeps what? Keeps running, because why? It sealed itself in. So I'm sure at Rosa you see a lot of push buttons. They probably simulated on a lot of HMI panels. But still, they still have push buttons, like e-stops and stuff like that. You can't simulate e-stops. E-stops cannot be software. E-stops have to be hardware. They got to be hardwired. So these are relays. This would represent, but I could just as well have come up on my relay let's come up here and do this, and I'll close this one. So this is a second circuit. So this relay is actually, it has one pole, and it would be a single pole double throw. Y'all understand those terms? Well, okay. So what it means is I could come over here and we'll put another line down here. I'm going to draw that. I'm going to call this CR1. This is CR1. That's CR1. So I would need 3 contacts on this relay, by the way. And I would come over here and would turn on another light. So let's say this is yellow and this is green. This is the symbol for normally open. This is a symbol for a normally closed contact. But all these contacts are being controlled by that one relay, right? So this is not a good example because I've only got two contacts. But how many contacts can a relay have? A few. At least one, right? You understand. But they could have many. I mean, we've got, huh? No, I'm talking about real contacts. I'm not talking about simulated contacts. So one of the primary languages that we program a PLC in would be in what we refer to as ladder language. So these are all normally open contacts. This is the start button. So the start button is a normally open contact, right? You understand? 4B1, we know that's a what? Sensor, right? And this would be 4B1. This would be B1, so that's the sensor on the bottom. So we're saying if 4B1 is true, right, and B1 is true, and the start is true. Now this gets people messed up because what we want, we've got a normally closed push button out there, right? You understand?
Just for that.
Yeah, this is for the first module right there. This is actually the first module. This would be the actual program for the first module. And what I did is I did the first program in function block programming, and I did it in sequential function block programming, and I did it in ladder. Because that's the three main languages. This is the guy right here. This guy right here is the guy. This is the primary language that we use to program PLCs is ladder. Why? Because there's a lot of people that understand it, and it makes sense, especially people that's come up through the electrical trade. And these right here, these are not actually coils. These are the symbols for coils. For some reason, Alan Bradley puts it inside of, I guess they did it because when they originally drew it, all you had was yeah, that's all they had on the keyboard on the computers that they did it. So that might have been, Alan Bradley's been around for a long time. If we looked at Siemens, the coils would actually be coils. They would be round. These are the rungs. They number the rungs. And this would be ladder. So it says if I press the start button, FB1, 4B1 is true, B1 is true, and the stop button is not pressed, then this coil right here would be energized. And so this would be an example of a PLC program. Now, of course, y'all are going to take PLCs and you'll get a lot more involved in this. But what we're going to do is we're looking at it from this right here. So this is assigned to an output right there. And by the way, 5000 does it a little different. This would be what we call a module number. And then this would be an output on that module. Yes, Q. Siemens uses Q. Alan Bradley uses O for output. Siemens decided to use Q. If you ever programmed an Alan Bradley PLC, one time you're going to substitute an O for a 0 or a 0 for an O. So what Siemens did is took away that feature. So they don't use an O for an output, they use a Q. They still use an I for an input. So here's I, slot 1, input data 2. So their addressing is quite a bit different than what we'll teach. But it's not that hard. We'll show y'all the difference in the two when you take advanced PLCs. Did we do that in this class? I don't remember. We did so much in that class. So there's three languages, but we're not in this class, we're not looking at how to program this thing, but because we're looking at it from a troubleshooting point of view. And of course, not from a programming troubleshoot, from a hardware troubleshooting point of view. Of course, we do teach programming languages too. So when we get into fluid power, what do we have? We have all these symbols that represents the different components in the fluid power system. So what's some of the components we have in a fluid power system? What's some of the components we have in a fluid power system? First of all, what is fluid power? What is fluid power? It's creating a force using a fluid, right? Everybody understand that? And of course, we have two types that we use. One of them's called hydraulics and one of them's called pneumatics. So how does hydraulics work? How does it create pressure? So to create a pressure, we have to create a force. So force is something that causes something to move, right? You understand that? To get a force, we have to have a pressure. And the amount of force we generate, anybody know the basic formula? Pressure times area. Yeah, area, or yeah. times pressure. So how much force we generate is how much pressure we have and how much area we push it against, right? So if I have 1 pound of pressure and I push it against 1 square inch of area, then I would create 1 pound of force. If I take that 1 pound of pressure and I push it against 2 square inches of area, I would create 2 pounds of force for 1 pound of pressure on my fluid. That makes sense? So we do hydraulics, we create a pressure with what? Liquid. Usually a what? Oil. This is uncompressible. We consider fluids to be uncompressible. We don't, every one of them compresses a little bit, but we wouldn't have the instruments to be able to measure what a fluid would compress. So from our point of view, fluids are uncompressible. I need to go get my syringe. We'll do that. And put some water in it and let y'all put it in there and try to push the plunger down on it with it stopped up. Allows extremely high pressure. So when we use fluids, usually we use extremely high pressures, which means the system itself is going to be expensive because all your hosing and everything is either going to have to be solid or it's going to have to be high pressure piping. And normally we have to have that high pressure tubing to go between something that's not moving and something that's moving, right? Understand? Or even vibrating. Allows very smooth motion. We can allow precise speed control. So how do we control? So pressure controls the force. What's the basic factor that determines the speed of an actuator? The pressure determines the force. So I could have a pressure of 1,000 psi, and that sucker might be moving at 1 inch per hour. Or I could have 1,000 psi, and it might be moving at 5 feet per second. So the pressure does not determine the speed. What determines the speed? Well, not the valve. The rate of the flow. How fast the fluid is moving. Right? Y'all understand that? So flow, we can control liquid a lot easier than we can control gas. Smaller actuators because it's force time area. So over here, if I'm running this thing, so the planes I worked on ran 3,000 psi. That was their hydraulic pumps. Ran 3,000 psi. And if you got up into the back of the tail of the plane and looked at these actuators that move these big old control surfaces, and I worked on a big airplane. Them suckers was only about this big. So they maybe had 2 inches worth of area. But with 3,000 pounds of air, that's 6,000 pounds of force I could create on those surfaces. Right? You understand that? So we run these things at extremely high pressures. Like I said, the planes it was 3,000 psi. You had to be careful around that stuff, guys. Because if it got a hairline leak on it, it could do what? Touch you. Yeah. So nobody wanted to get down while the plane was running. Very efficient to operate. The problem is it's got to be a closed system. Why? Don't know what we mean by closed system. So we got to have a tank that's got the fluid in it. We got to have some type of pump, right? Then we got to send it out, go through our actuators, and then do what? Well, it could be a cylinder, it could be a motor. What is an actuator? An actuator is a device that takes this pressure and converts it into motion. That's what an actuator is. So we got 2 types of actuators. We got either rotary actuators or we got what? Linear actuators. All your cylinders are going to be linear actuators. And then we got hydraulic motors. So we got fluid power motors. Anybody that's got an impact rig, that's a what? That's a fluid power motor. Right? Pneumatic. I haven't seen a hydraulic one. I'm sure they're out there because they can create so much force. The cons, of course, we got to worry about what? Loud leaks. Then we're going to have to worry about the danger of such a high pressure, right, getting loose. And of course, it's expensive to install and maintain. So we need to get up to pneumatics. What's pneumatics? Well, gas. Normally we use air, but I've had a system before that used nitrogen. So it uses a gas. It was a system that actually
Compressed nitrogen.
huh?
Compressed nitrogen.
Well, what's nice about natural what's nice about people don't understand it. They don't put air in airplane tires. They put nitrogen there. Why? Well, it doesn't expand and contract as much as with temperature. Air has a real wide expansion and contraction. So nitrogen, we wouldn't have to worry about that, about it expanding and contracting with temperature. Yeah, we got a gripe one time. I was in electronics, but the guy in the major showed me where the guy landed and they said put re-air tires, because they got to a place and one of their tires was low and they had to put regular air in the tires. So they couldn't get up above 10,000 feet. They had to fly all the way home below 10,000 feet so the tires wouldn't blow up on them.
Usually you'll see the nitrogen tanks, they're compressors, they're like carbon fiber. Why is that?
I don't know. You got me. That's something I didn't know. The compressors?
Like when they have tanks of nitrogen, it's like a carbon fiber tank.
Oh, really?
Instead of
I didn't know that.
yeah, like paintball. But
Well, no, I played paintball for years, and ours was just metal. We used CO2. We didn't use nitrogen. We used CO2.
yeah, they sell nitrogen for paintball.
Oh, really? No, we
All the
used.
tanks are,
I still got my paintball gun.
Yeah. You ever got here in Alabama before?
No, we had our own field. We had our own wooded area, and it used to be big by my house. We had our own field tanks,
I love it.
and we had our own field tanks and everything. We used to play every Sunday after church. So, but create pressure with gases must be compressed before we use it. So gases are very compressible, right? You understand that? So we have to compress it before we use it. Cheaper to install in hydraulic systems. It's safer because the pressures are lower. Because we can't have extremely high pressures, because what happens when we pressurize gases? They turn into liquids. Yeah. So gases turn into liquids. So we can't run them at extremely high pressure because they would turn into what? They would turn into liquids, very cold liquids too. But what another big advantage, it saves us a lot of money, because if we use air as the gas, if we use something like nitrogen or something like that, then it's going to be more expensive. If we use air, which is the predominant gas that's used, then what can we do when we're through with it? Just shoot it back out in the air, right? So that saves us a lot of money, so we don't have to have these return lines coming back to the tank. So this is the tank right here. Then we put it into a reservoir. The problem we have is inefficient, releases moisture when compressed, very jerky, because why? It's constantly trying to uncompress. So if I move it, and I move into a cylinder and it comes up against the cylinder, it's going to try to uncompress, right? So cylinders try to be very jerky, and it's difficult to control the speed. So if I don't need precise speed control, and I'm not worried about real jerky motion, then this is the route to go, because it's so cheap to install, easy to maintain, right? Parts are very cheap. So y'all have any hydraulics out there? Sure. Stuff that really, really requires heavy work. So instead of me using a cylinder this big, I can use a cylinder that big, right? You understand? You get a lot of work out of it. So yeah, anything that requires a lot of force, then odds are we're going to use hydraulics. Anything that can run 100 psi or below, we'll probably use pneumatics. Because here the cylinders are still not really big, right? You understand? They're still manageable. So typical systems, on a hydraulic system, we have what they refer to as a reservoir. We have a pump, we have piping, then we have some type of control, right? So we can control the flow. This is where our directional control valves come into play, where we can either turn the flow on or turn the flow off, or we can control the direction, so we can make a motor run clockwise or counterclockwise, or we can make a cylinder extend or retract. And then we have the actuator. The actuator, what's out on the end. This is The guy that does what? Turns what? The pressure into motion. Pneumatics, we have to start off with a what? Compressor. Then we have a tank that we store that pressure in, right? Then we have piping. It's usually what? Plastic. Then we're still going to have control. We've got to control the flow, right? You understand? And then we're going to have actually have the actuator. But what we don't have to have, of course, is we don't have to have the return line, right? Everybody okay? Any questions? So y'all hear our compressor running in there every once in a while. We got a dual stage compressor back there. It puts out around 250 psi. We don't use that much. Reservoir holds sufficient liquids to meet the system demand. So what you're supposed to do is you're supposed to have a level in there so you can keep the pump from cavitating with all your actuators fully extended. And that's what you're supposed to put. And we can also put things in there to condition, right? Okay? Heat exchanger. Anytime we compress something or anytime we flow it, it has a tendency to get hot, right? Compressors are real bad. So anytime you take air and you compress it, it's going to get what? Hot. It's going to heat up. And it's also going to release moisture. And we got two problems. We get moisture. Not only do we get moisture from compressing it, but once we get it into the tank and it starts chilling down, what's it going to do? It's going to release moisture too, right? You understand? So that means on this pneumatic system, we need to make sure we come up with some system where we manually go out and drain that compressor, not the compressor, the tank constantly, right? You can hear this one. This one automatically drains. Everyone probably goes, psst. Yeah, so this guy's it automatically bleeds this guy off, which is neat. Huh? Having to go through all the tanks and drain them. Some of them will actually have U shapes in the lines. It's a sump basically that you can drain too. They do that a lot, especially in steam systems. Ensure that ensure a high enough fluid level that when all actuators are extended, there's not a whirlpool effect of pump suction. Have enough airspace when all actuators are full, retracted for thermal expansion. Shape tall and narrow is preferably to wide and flat. We okay? We okay? Parts, we have some type of indicator on the side of the reservoir that lets us know when it's got the proper level in it, right? It's also going to have some type of hole that you can keep, that you can do what? A filler where you can do what? Add liquids to it. It's going to have some type of breather, because if you seal that sucker up and the fluid tries to drop down, if it can't get air to come in the top, it's not going to work, right? You understand that? So it's got to have some type of breather that lets air in so the fluid can rise and do what? Can go down and do what? Come back up and the air will. It's got baffles in it. Baffles are just nothing but ridges to keep when the return comes back in, to keep the from creating waves inside the. Anybody ever sleep on a waterbed? Motionless and motion, full motion. So motionless had a bunch of baffles inside of it. So when you lay down it, the water didn't just move and start bouncing from each side. It was baffled, right? You understand? So if you ever took one of those apart, you see it had a bunch of liners in it, with a bunch of holes in it. Full motion, you jump on the thing and it do what? You'd be going like this for about 30 minutes, yeah. A drain plug, gotta have a drain plug, right? Every once in a while, we're going to have to drain all that oil out and replace it. Temperature gauge and some type of filter so when it comes back. So usually the return will come back and it'll drop in on the top and it'll fall through a filter just to get rid of any garbage that gets in and inside the system. Okay? So this is a typical setup. The pump, the level gauge, right? This has got a cooler on it, though, by the way. I don't think it's fans inside. And then a big old hole so we can take it apart. This is probably the drain plug down here, and we can't see the filler. Hydraulic piping. So a lot of your hydraulic piping, if it's not going to move, it's going to be metal. If it's going to have to move, there's going to have to be high pressure lines. It's kind of like if you got an air conditioner in your car, everybody does. And if you lose those high pressure linings that run, so if you look at your air conditioning system, the only place you got flexible hosing is when it runs from the motor up to the actual compressor itself, because it's constantly moving. If you ever have to place one of those guys, you better get out your checkbook, guys, because they are expensive. Those high pressure things. This is my compressor, by the way, out in the house. I got a crap. Same one with me. This is oil free. So some of your compressors, if we looked at this compressor in here, it's got a dipstick on it that we have to keep that sucker oiled up because it's a motor, right? Right. So it's a reciprocating compressor. This is too. You know what reciprocating means, right? It's got pistons and they move up and down. This is actually the specs on mine, by the way. Color is red. Motor operating. So this guy can operate to what? 150 psi. This guy can deliver 400 cubic feet per minute, standard cubic feet per minute. Why they do standard cubic feet per minute is standard cubic feet per minute is what the compressor could deliver if it was operating at sea level. Because the problem you have is the higher you get up, the thinner the air gets, and the compressor can't move any more than it moves, right? You understand that? So this standard cubic feet per minute means that's what this compressor could do if it's at sea level. So here, we could probably have some math formula, we could figure that out. This is only at 5.1 cubic feet per minute at 40 psi, but only what? 3.8 if you're operating at 90 psi. So this would be our flow rate. So our actuators would move faster at 40 psi, but they wouldn't be able to generate as much force, right? You understand? And they would operate slower at 90 psi if we operated at 90 psi, but they would only move at whatever 3.8 cubic feet per minute. Cubic feet per minute. Are we okay? Make sense? As gases are compressed or generate pressure, they heat, right? Air cooling, liquids cooling. So what we do inside some of your compressors, and we'll go here in a minute and look at this big compressor in here. And if we have multiple stages, and you can tell if you got multiple stages means we can only get, and they're going to have fins on them, right? You understand? Just like a motorcycle would. And what you'll do is you'll have a tube here, or a cylinder here, and then over here you would have another one, and it's going to be smaller. And then what you do is you take the output of this guy and you feed it to the input of that one. So that's why the other one has to be smaller, because you're taking something that's compressed, and if you put it into a chamber the same size, it would uncompress again, right? And then, but this gets real hot, so somehow we need to be able to do what? To cool this off when it goes from compressor to compressor. This would be what they call an intercooler. An aftercooler, this would be the guy right here that feeds the tank. And this is where our aftercooler would be at. It'd either be in here, but usually it's out in here somewhere. Now my little compressor doesn't have that. All it's got is fins. It's just a single cylinder compressor, right? And so it's just depending on copper pipe running from down into the tank because of that. Filters. So we have to have filters. This is something, y'all saw the filter canister up at the top, right? Got to filter the air. We don't want this dirt to get inside our cylinders, because if it got in there, then your rings and everything would wear out real fast. Just like your filter on your car. These are after chillers or after coolers. Some of them have water in them. Some of them they don't. Ours is just a big fin thing, right, that blows the fan through it. Reservoirs or tanks. Everybody okay there? This is the piping that we use. Usually what can be metal. Also, if we're running through very harsh or rugged environments where people come flying through there in forklifts and all that other kind of stuff, odds are we'll probably use metal, because if they hit it with a forklift and it was plastic, they'd probably do what? Break it. Inside the system, though, where it's safe and everything, they'll probably use plastic. We use a lot of quick disconnects. These guys right here. So they're very, very easy to replace when they go bad, or you could run solids like this. All right. So all this over here is quick disconnects. So the way these things work. The way these things work is that you just take the pipe and cut it flush on one side, you stick it into there till it bottoms out, and then you're okay. To take it out though, you have to push the blue collar down to pull it out. And you cannot do that when it's under water pressure. Well, you can, but you have to be really working. So these are quick disconnects. Guess what they call this? They call it a T. If y'all take the fluid power class, I'm not sure if Rose will come to take that class. Is fluid power part of y'all's program? Is fluid power part of y'all's program?
We don't have a clue what we're doing.
They call it hydraulic
2 months at a
pneumatics
time.
on package.
We're not informed. Yeah, that's exactly right.
So you can say, Rich, I don't know. I don't know if I should give that to you or not. Because I don't think Mike and CJ has gave us permission. But as soon as they do, guys, I'll give y'all a copy of the plan. This is a typical pneumatic system. This could also be a fluid power system. By the way, we do have a fluid power, so this is what you on pneumatics. You definitely got to bleed the pressure off, right? You understand that? Because this sucker stores pressure, right? You understand that? So just because you go out there and you turn off that compressor, you can still have problems, right? You understand that? Hydraulics, there's a lot of hydraulic systems. They use something called an accumulator. An accumulator is nothing but a big old tank. It's usually vertical. And it's either got a big spring in it or it's got a big counterweight in it. When you put the system on, what it does is it fills that accumulator up. And what it does, it acts like it takes ripples out of the fluid, makes the fluid really, really smooth. But it also, when you turn the system off, the weight of that spring or that weight of that big weight that's sitting up there keeps pressure on the system. And this way you don't have things opening up and closing and doing stuff like that just because you turn off the pump, right? You understand? So if you're in a hydraulic system that's got that's got an accumulator on it, you're going to have to bleed that or disconnect or do something with that accumulator first. And I don't know if they have those at Rose or not. It wouldn't surprise me if they didn't, because y'all got a lot of things down there that if power fails, you don't want things to open and fall and do stuff like that on your hydraulics. And that's what the accumulator does. So it maintains pressure even when there's even when the pump's not running. Okay, so we already looked at this. So this is a typical diagram for a fluid power system. So we have a circuit. Each circuit controls some type of actuator, right? Understand. We start at the bottom. This is what we call our service unit. Notice it feeds everybody, so it doesn't have all its numbers are what? 0, right? Understand. So what does a service unit do? Well, this is a symbol for a filter with a drain. This is a symbol of a pressure regulator. Adjustable. See, anytime we see an arrow moving through a symbol, it means it's what? It means it's adjustable. And what do you think this is a symbol for? Good. G-A-G-E or G-A-U-G, whichever one you spell. This is a symbol of your disconnect. This is a valve. How many positions does this valve have? It's only got 2 blocks, guys. So it's got 2 positions. How many ports does it have? 3. One, 2, 3. So this is actually what's venting off your pressure. So 3 is what you hear when you turn it off. That's what you're going, because what you're doing is you're shifting it over 3, and what it does is it vents the pressure off. Right? You understand?
What's that? I didn't just write down quite what you have. That one symbol beside the filter. The one directed to the right of it.
Y'all got a handout, by the way, that shows all these symbols and gives y'all their name. So this is the what? No, it's on it. It should be in the handout sections under symbols. So what do you say? What do you say, Grayson? This guy?
Sir.
This guy or this guy?
That one.
This is the pressure regulator. It's actually an adjustable pressure regulator. So that means we got the cap. And what you have to do on these guys to adjust it, you have to keep them from accidentally turning. What you have to do on most of these is you have to pull them up. Then you can adjust them. When you get through, you're supposed to lock them back down, right? And that way somebody can't accidentally do this. And what do we say this was? Filter with it. So what we're doing, we call this a service unit because we could have all these things individually, but these things are all built in one unit. This right here is e-stop, but it's actually manually operated. So that's what this guy right here means. This means it's manually operated, right? And it's a 3 two-way valve. With detents. So these are your detents right here. See that little old dash right there? That means it locks in the detent, the little dash. Are we okay? So y'all have already played around with that, right? So we go over here, if we push down on this, and what would happen, if we shift it down here, we'd take 2 and push it out, and it'd go out there, and it just vents out. And that's what you hear every time y'all push that e-stop in, right? Or the stop. And then, of course, now we come up, and this is the manifold, that big black box, or that big black cube that's under that. It comes up here and runs down through the manifold. So there would be our pressure, right? So pressure is sitting up here on all these valves. These are all core two-way valves. They're all solenoid operated. In fact, this would be a double solenoid operated. This would be a single solenoid operated, right? With manual override. So here's the manual override. I'm sorry. Duh. So these are the manual overrides. So there's one there, here's one right here, here's one right here. Now notice this has got manual overrides on both sides. This is single solenoid operated with spring return. Are you okay with that? So this is basically what the line puts together. Puts a four two-way valve together. It's manually operated with spring return. Are we okay? Any questions? Everybody okay so far? Yes? And what you have to do, of course, in your head is do what? When this solenoid operates, in your head, you got a picture of this whole valve moving in that direction. So what happens is this block moves against the spring, and then this block right here lines up. That's what you got to do. That's one of the hardest things for people in this to see. So right now, what would happen is pressure would come up through here. Now, this is the symbol of what we call a check valve. And they do it different ways, but no matter how they do it, this is the symbol they do it. We got a ball, then we got a V shape like that. So what happens if fluid goes on this side, it pushes the ball up out of the seat, right? You understand, and lets the air go through. If it tries to come the other way, then it pushes the ball into the seat and it can't go. So these are check valves. Check valves are valves that only lets the fluid flow in one direction, right? This right here is an adjustable flow control valve. So what do we use the flow control valve to? To control the watt of the actuator, the speed of the actuator. Now, unfortunately, they drop a little pressure, but once the thing's fully extended and everything goes out of motion, you get full pressure. So what happens is that what we want to do, what happens right now, we'd come over here, and of course the fluid's going to take the path of least resistance, so all your flow is going to go this way. Then it's going to go up, it's going to push against this piston. That's going to cause this guy to move. All the air that was over here is going to be vented, right? It can't go that way. This has got to go to the flow control. Then it comes back, goes through here, and what do you think that's the symbol for? That's the symbol for the exhaust. Now what we're doing, this is referred to as meter out, which we do in high. So what we're doing is we're controlling the flow of the exhaust. We do this in pneumatics on double acting cylinders. We can't do it on single acting cylinders, but on double acting cylinders, we like to meter out. Why?
Cylinder don't get stuck.
Well, what's happening if we metered in, this guy would come up here and push, the air would move, the air would uncompress because it's not pushing against anything, right? Then the air would compress, then it would move and the air would compress. So what we're doing with this meter out is we're constantly putting back pressure into the exhaust. So we're not letting the exhaust flow out real fast. So what it means is this pressure is always pushing against something. So this guy is holding it, this guy is pushing, and what it does is it makes the cylinder move smooth. If we didn't do that, then the cylinder would be what? Would be jerky. Because as soon as it moved, the gas would do what? It would uncompress, right? You understand? And then it would pressurize again. So pneumatics, on double acting cylinders on pneumatics, we always meter out, which means we meter the exhaust. And you can tell by looking at the check valve. So this is a flow control valve, or a lot of people call it a one-way flow control valve, because we only control the flow in one direction and we bypass it in the other, right? You understand? What we do is we just look at the check valve. If that V is pointing away from the actuator, then we're metering out. If it points toward the actuator, it's what? Meter in. Hydraulics, you don't care. Hydraulics, you meter in or meter out, it don't make any difference to hydraulics. Because hydraulics don't uncompress, right? You understand that. But on pneumatics, on double acting cylinders, we will meter out. Now this guy right here, guys, this is a symbol of a magnet. If you remember, that's a symbol of a magnetic. So if I've got a, oops, sorry, wrong symbol, thinking wrong. So if I've got a symbol of a sensor, right, we come up here and put this, then we come down here and put some type of symbol. So if we put this at the bottom, it means it senses a magnetic field. So what this means is this cylinder has a magnet in it. It's mounted on the piston itself. And it's pneumatics. So pneumatics, it means the metal that we use on these things are going to be aluminum. Aluminum has very little effect on magnetic fields. So what that means is I can put a magnetic sensor right there, right? Like a Hall effect, or I can use a reed switch to sense when the thing is either what? Extended or retracted or wherever I want it to. So that's what every one of these cylinders has what in them? They have magnets in them. Are we okay? Any questions so far? So if we were going to do what? If I was going to extend it, or if I was going to come over and extend it, then I would come over here. I could either use the manual override, right? And they're not easy to get to, guys. They don't want you to easily get into these things. Why? Because people will be pushing on them all the time. So these are not going to be buttons sticking out. They're going to be recessed. And usually you got to get something that's got a point on it and stick it in there to override these things. So they're not easy to override, because people can get killed real easy by some guy come over and say, what does this button do, right? And some guy would do that, right? So I would come over here. Normal way we would do this is we'd energize the solenoid. It would cause this whole thing to do what? Shift, which would cause this now to line up with this one. It's going to bypass it. It's going to put pressure there. Here comes our exhaust. This is going to line up, and it's going to line up like that, right? You'll see that? And so we're metering out both ways. We're metering the exhaust both ways. So we've already talked about this. So how do we call these things? From left to right, the way these cylinders are, the way these actuators are laid out on the line. So the first one you see would be this guy right here. So we draw it, we try to draw it the way they're actually laid out on the module themselves, right? So this is actuator. So A means what? Actuator. So this is the first one on the left. So this is one, actuator 1 or 1A. Then everything that's in that circuit starts off with what? 1. So M is a what? Solenoid, right? V are what? Valves. A is what? Actuators, and B's are what? Sensors. Now they don't show the electrical circuit of the sensor because this is not the electrical circuit. This is the pneumatic circuit. If we wanted to know what this sensor hooked up to or what input we have to look at the electrical diagram, right? So here we come up this one. This is actuator what? 2. This is actually our it's technically not an actuator because it's not converting it into motion. It's generating a vacuum. This is a, what's this right here? It's a pressure control valve, so we can control the pressure. Okay. This right here is a what? Gauge. So gauges are what? Z's, right? This is the actual ventura that generates the pressure. That's a silencer, by the way. And this is the little suction cup. This is our pressure switch right here. I'm sorry, this is our pressure switch right here. This is an analog pressure switch right here. So not only does it give us an indication of when the pressure is at a preset, this means that this one is what? Adjustable. So we can set the pressure on it. And this is a knob people can turn with their fingernails. So guess what? It's going to happen sooner or later. Somebody's going to change it, right? And these are basically the same. So this would be a 2, this would be a 4 two-way valve. So we start off with the number of ways, right? Then we put a slash, we put the number of positions, then we say way. Now how they came up with that, I don't know, but it sounds cool. Double solenoid operated, manual override, right? Everybody okay with that one? We know these are, now these are called 3 because this is the third actuator in the system. This is a rodless cylinder. It does not have a rod on it. And so we'll look at rodless cylinders later on, but rodless cylinders, the actual piston or the actuator, the guy that actually moves on this one is clamped with magnets. And what advantage does a rodless cylinder have over a rodless cylinder? I mean a rotted cylinder. The problem we have with actuators in long strokes. What is a stroke of an actuator? How far it can extend, right? Well, the problem is if I needed 12 inches of extension, that means the cylinder itself would have to be bigger than 12 inches, right? You understand? And then I'd have 12 inches out this way. So that means this sucker right here is going to occupy 24 inches worth of space. Plus, the longer you get that rod out there, the more tendency it's going to have to bend on you, right? You understand? Because you're trying to generate force with a rod that's sticking out there. So, you know, if you look at your jack, if you got a hydraulic jack, it's got a real big rod on it, but it only extends out that far, right? You understand? If we was to take that and put it up 4 feet, then odds are it would bend trying to lift the car. So what's nice about a rodless cylinder, basically the only thing that limits the stroke on a rodless cylinder is how far your cylinder goes. And plus another thing, if you need a 12-inch stroke, then you're going to almost occupy only about what? 12 inches of space. So extremely long strokes, then we like to use rodless, but sometimes we can't. You ought to see the cylinders. Used to you could get down to the locks and dams. This is before 9/11, and you could go down the Warrior River. You could come in and you could walk right up on them locks and dams and see the big actuators. They had graded floors out there and look and see the hydraulic actuators that actually open and close that little gate. Those are hydraulic. So we could not use a rodless cylinder to generate that much force. But the force that we're generating, rodless cylinders work real well. These are actually running our gantry robot right here. So that's 2 magnets. So this latches on magnetically. I've seen them use straps coming out. I've seen them use chains coming out. And so they actually move a chain. All the ones we have on our line is magnetic. Everybody okay with single acting cylinders and double acting cylinders? With single acting cylinders, we're going to use force. Now this guy right here, if we're going to control the speed of this guy, we're going to have to meter in. And of course, what do we do with a single acting cylinder? We use force to push it one way, and then something else brings it back, right? Everybody okay? A double acting cylinder, though, what? We use our pressure to move it both extend it or retract it or cause it to go left or right, depending on what type of actuator it is. Are we okay? Question? This is the inside of a cylinder. So this is our cylinder right here. What does our cylinder have on it? Magnet. So now we can use external magnetic sensors to sense when this thing's in a certain position. And sometimes those are adjustable, which means somebody can do what? They can adjust them. And you'd be surprised, people get out there not knowing what they're doing, and something stops working. So what do they start doing? They adjust knobs. We used to call them knob dickers. True story. These are rodlet cylinders. So we have a carriage somehow that clamps onto the piston that's moving, right? And they do it different ways. Cylinders are slightly longer than the stroke. So your rodded cylinders, you got to have space for the mouth of what? The cylinder and the rod. You got to have space for the rod. They take up a lot less space. Now, these are rotary actuators. We do have one of these on our on the Festo line. So we can have what they call a vane actuator. So you can see what happens here. We put force in one way, it goes to the left. We put force on the other way, it goes to the right. Or we could have what they call a rack and pinion. A rack and pinion is a device that takes a rotary motion and converts it into a linear motion, or vice versa. So ours is vice versa. So what we have is we have a rack, which would be nothing but a linear gear. Trying to do this sideways here. And so it would have a linear gear on it. And then we have a pinion, which is the gear that rests down in here. So this is the way that flipping robot works on the Amatro line. So what it does, it's got a double acting cylinder up here, and when it pushes it one way, it takes the rack and moves it some way and causes the what? Causes the rotary gear or the pinion to turn. Or we could do it the other way. Like the old steering wheels on cars. This is the way cars used to steer. So you turned your wheel, you moved the pinion, and then it had the rack that actually did what? Turn your wheel. Now it's directional control valves. Oh, y'all okay on that? So identified by the number of positions the valve can be moved through, 2 or 3. So the maximum we'll ever have is 3. So what they'll do, a 3-position valve will look like this, and we don't have any 3-position valves over here. So we have a center, and we get different centers. We have what they call floating centers, locking centers, depending on what we want to do. So these valves are either going to have what? 2 positions, or they're going to have what? 3. And I'll try to show y'all some centers. The ports it's going to have 2, at least 2, right? It's got to have an inlet and an outlet port. It could have 3, 4, or even 5. The only way you're going to see a 5-position valve is if it's a 3-way valve and they have 2 exhausts. And what it does, the exhausts have the same distance to travel. So if we got one exhaust, it might be down on the left-hand side of the cylinder, on the valve. And so this guy would have to exhaust all the way through a tube over to here, right? So what would happen is the flow wouldn't be the same for both extending and retracting. So a 5-port valve basically has 2 exhausts. It has 2 exhaust ports. So that means both ways has a what? Has an exhaust. The number of ways how the valve is moved into position. So we have what? We have manual, we have mechanical, we have solenoid, and we have spring. The nomenclature is you say the number of ways, so that's the port. So ways are also they call it ports, but basically ways is the ways that the fluid can flow. So every port would be considered a way. But the way we say is we say ways, position, then we say what? Way. Does that make sense? So a two-position, four-port valve, we'd say a four two-way valve. That's the way you would order them. That's the way you would say it. So you don't see anybody that's been working on it that would say a four-port, two-position valve. You don't hear anybody say that. That hadn't been in the field there. And if you looked up and you ordered them out of a catalog, they wouldn't be that way either, right? We've already saw the directions were drawn in the initial. So anytime we're going to draw these things, we're going to draw them in their initial condition according to the system that they're operating in, right? So when we go over there and we hit reset, that's the way these valves will be drawn for this system. You can hear them. You can hear them shift, right? So if something's extended or something, you reset it, everything goes back to the initial position. Are we okay? Questions? Answers? Directional control valve. So we understand how they work now, right? So this guy in the center, this is called a spool. You can see how it got the name because it kind of looks like a spool that people sew with, right? That threads on. So the actual thing in the center of the valve or inside the valve that controls the direction of the fluid, that's called the spool. This is a hydraulic valve, by the way. So this T stands for tank. T is pressure, and the ports are on that. So this would be a three. So look at this guy over here. So that would be a three-position valve. With a manually operated, see that symbol? Manually operated. This has got a check valve in it, guys. I've never seen that before. That's pretty neat. This would be a three-position valve, right? How many ports? 4. So this would be a 4 three-way valve. And we'd say this would be what we call a closed center. This is what we would have to use in pneumatics. We use a lot of this in fluid power because if you're not using the pressure, then what you would like to do is you would like to return it to tank. But pneumatics, we can't return it to air because we lose our compressor. So these are all hydraulic. So here what this would do, if we put it in the center position, it would maintain pressure, right? You understand that? But it would lock the actuator. So the actuator wouldn't be able to exhaust and the actuator wouldn't be able to move. We couldn't extend it or retract it. You'll see this done a lot on actuators that we stop in mid-range. So if you're out there working on a backhoe and you're moving that thing around, that's got to be a three-position valve because you can stop that thing anyway and it holds its position, right?
The top one is closed center.
It's closed center.
Bottom.
The bottom is what we call a tandem center. Yeah. Because it returns the pressure to the tank and locks the actuator. So if the actuator can't exhaust and the actuator can't move, right, the fluid can't move, then the actuator would stop. Hydraulics, you would not be able to move that actuator. It would be locked in its position. And I see, like I was talking about a backhoe, what can they do on that thing? They can stop it anywhere, and it just does what? It just locks position. And if you go out there, you couldn't pick it up and you couldn't pick it down. Pneumatics, by the way, even a closed center, you would be able to move it a little bit because you can compress it a little bit, right? You understand? So this is another problem we have with pneumatics is we can't lock the actuator in mid stroke. Right? We can, but it still might do what? Move a little bit because we can compress it. But yeah, anybody that's seen people run a backhoe, they can stop them hydraulic valves where? Anywhere. And what does the actuators do? They just do what? They just lock. Or dump trucks. They can do what with a dump truck? They can just stop it anywhere though. And it just does, it don't go back down, it don't go back up. And those are the closed center valves.
It does need to take it.
Yeah, you do. It means you got a leaking. It means usually means your cylinder's got leaks in it. So this is an animation that I made. So this is what you got to visualize. So it's drawn in its what? In its reset position. And this is what you got to do is you got to position, you got to picture this thing in your head doing what? Shifting over.
Because the symbol itself is not going to shift. You have to picture it doing what? Shifting over. I did that. Cutting, a bunch of cut and pasting and lining up. So these are some valves. We can see them over there. Ours don't use big solenoids. Ours use very small solenoids. And ours usually is pilot operated. We're going to get into this. Pilot operated means you have a little tiny valve that opens, so your solenoid opens up a little valve, and then it uses the pressure to move the spool. So magnet operated, solenoid. What's nice about solenoid operated? Well, what's the advantage of solenoid operated over magnet? We can turn those over to control systems, right? So now we can go into automation. And these are what's up on the chart right here. So if you look in your handout session, it says symbols. Now this is no way close to all the symbols that we have. These, I mean, that's out there. But these are the symbols that we run into in this class. Do you got any questions on any of them? So all our valves, I think all our valves, no, the disconnect is a 3-port valve. But I think all our other valves in our whole system are 4-port valves. Now these are, see if we got another one. No. Any questions on this? So let's go over to the lines. This is up on Blackboard. So this is the one we just got through looking at, right? It's got all our pneumatic symbols on it that we'll be using. And then of course here's the one that's got our sensor symbols on it. Symbols all the time. So learning the symbols of your trade is very, very important because most of your drawings that you're going to see are going to use symbols, right? Because they take up a lot less space than trying to draw pictures. Now the problem is they call it pictorial drawing. So when you go out and buy like a new TV or something, they show you the TV and then they show you pictures, all this kind of stuff you look up because that's going into a commercial situation, right, where people don't understand this. Once you get into a trade, though, your drawings are going to be done with symbols. So we teach a class called Blueprint Reading, which we try to teach you the symbols of a bunch of different trades. So where did I get this from?
Handouts.
Yeah, this is Blackboard in the handout section. So we got the dictionary up here too that I've been working on. So it's still draft. It's got, so the way it's set up is it's got different sections. So instead of try to jumble them all together, I decided to put them in different sections. So if you wanted to look at fluid power, you wouldn't have to find them. You just go to page 24, and that should be all the terms about fluid power, right? Okay. So let's so all these drawings, by the way, and they will be up there. Of course, I got them cut off now, so y'all won't what? You look at them, right? But as soon as we get through with this, I'll come back in and open this section back up. So here's all the documentation that we get with the manufacturing line, the Amatrol line. These are the module numbers. The overview of what the module does, the components, the figures, the PLC I/O connections. Oh, this is not the one. This is
Can't
the,
relate this year, so
Huh?
put you on the team.
that's it. But I will get you on there. Guys, I don't, oh, here we go, electrical diagram. I was looking for PLC. So this is where all our symbols come into play, right? We explained this to you, are you okay there? Okay. So this is that gray terminal board right there, right? The cable plugs into the top that y'all been, not the little old 9. This is the little 9 pin right here. This is where the stations communicate with each other, right? That's the little 9 pin DB9 connectors that they have on the top. And then this, now notice this means, so this is plus DC right here. Okay. I don't know how to unzoom it. I need to, there we go. So this is plus DC right here, right? It comes up and goes through the whole system. Notice every switch is connected to plus DC. So these are momentary contact push buttons, right? This is what? This is normally open. This is our stop button. Stop buttons are what? Normally closed. Why do we want to use the normally closed push button as a stop button? Well, we could do it with a normally open. With a PLC, don't care. But what normally we use normally opens, normally closed, because if something happens and that wire breaks, then the system will stop. If it was normally open and the wire break, then you couldn't do what? You couldn't turn it off, yeah. So these guys are hooked up to source, right? You understand that? They're all using a positive common. Are we okay? So that means the PLC has to be considered to do what? So the PLC has to be synced, because the inputs are sourced. You understand those terms? So that means if I buy a sensor for this PLC, it's got to be a sourcing sensor, which is the what? So we have two types. We have NPN and PNP. PNP, this thing's not drawn. These sensors are what? No, NPNs are syncing. And PNPs are sourcing. I'm going to draw it out. And trouble is, they don't tell you by the symbol. It's how the things are connected on the inside. So this switch would come down here and go to input 0, right? Input module 0, even though we don't see modules, it still works that way. And this would be in the actual 0. This would be input 0, the first port. This would be the second port, third port. Now notice we start numbering it with 0. So you'll find out in computers that 0 means something. So we use the, like a lot of times on a football team, the kicker will be 0. It don't mean the kicker doesn't exist, right? You understand? It doesn't mean the kicker doesn't have weight. That's his address. That's his number. And these are the outputs. So the outputs, we have to use sourcing input devices because our PLC is set up to what? Sync. In fact, we can't change that on this PLC. And this is one of our sensors. Now these sensors have to be powered, so we can't tell from the symbol. We can't tell from the symbol if it's syncing or sourcing, so you're going to have to know this about your PLC, right? Understand? Because these sensors have to be powered, and they're going to have to hook up. So I was right. Today, I need to tell this to my class. So here, this sensor right here, it's got to be powered, so it's got to hook up to both the watt, the plus, and the minus. So that's the minus there. So is it syncing or sourcing? Well, you can't tell because it's got to be powered up, right? You understand that? So this is where you're going to have to know what type of input your PLC uses. So we're using a Siemens 314. S7 314. Now you can't configure its ports like you can the Allen Bradley. So this guy runs syncing inputs and sourcing output. And look at the numbers. And we'll look at the color code too. So this is plus. Oh, I don't need to do that. I just need to change colors. So plus is going to be brown. So we can look at the terminal box on this. The minus is going to be blue. And then the signal wire is going to be black. And that's the standard color code for these sensors. If it's a single output sensor, if it's a single pole, y'all understand single pole double throw? We talked about that before. Well, some of your sensors have a single pole double throw output. They will only have one pole. I've never seen a solid state sensor with more than one pole. But it can have a single pole double throw. And the normally closed will use a white wire. And what pin number would it be? What's pin numbers missing over here? 2, good. And then the normally open will be a black wire. And that's the standard color code for these leads coming out. So you'll know that now, right? And I don't think there's a standard for your output devices because they can be, are we okay? So plus is what? 1, and it's brown. Minus is 3 and it's blue. So your power are your odd pins and your signals are your even pins, right? Are we okay? The black would be normally open. The white would be normally closed. Here's our outputs. So H3, what is H now? So we picked up another designator. What's that a symbol for? It's green over there. You have to push it over there. It's not the push button. It's the light in the push button. So H in this is for a light bulb, and that's a symbol for a light or an indicator. You don't have to be a light bulb. It can be an LED. These are drawn wrong. So these should have slants across them. I got to figure out what I'm doing. I'm glad to cause it to zoom in. So these should have slants across them, because that symbol without the slants is a relay port. What are these a symbol for? So these are the solenoids, and that right there is the symbol for the valve. So we know that we don't know the valve number because this is the electrical diagram. This is not the pneumatic diagram. But we do know we can look up what 3 on 1, 3 and 2 is connected to. That would be by the valve. I do know the one on the left is a double solenoid actuated valve. And I know this right here is a single. This has got to be a single solenoid with a spring returner, right? Are you okay? Everybody okay? And all these symbols are on those two sheets. One of them's called electrical and one of them's called pneumatic. This will be on the electrical symbol. So what we'll find out is this first print on all the modules are going to be the same. So there's our start button, there's our stop button, there's our e-stop button. So notice the difference between an e-stop button and a regular momentary contact push button. It's got the mushroom head on it, right? The little line right there means it's latching, and then that means it's got a detent in it. This is a symbol for a limit switch. So we know what a limit switch is now, right? So for S. So S means it's some type of limit switch, right? Are you okay? Are we okay? This is the way you're going to be able to tell the difference between a Hall effect sensor and a and a reed switch. A reed switch only has 2 wires. And so it's powering up through the load itself, right? In fact, it don't really require any power. But this switches us around, so notice 1 goes back to plus, and 3, which would be a black wire, which would be a blue wire, is now your signal wire. So this is going to swap around. I wish I'd have shown you that on the other one. Let me bring up the other one.
So the signal wire is going to be blue instead of black.
Yeah, because it's the power lead for the sensor. So this guy is the magnetic reed switch is basically not powered up, right? You understand? So its signal wire is actually considered also its power wire. If that makes sense. It does to me, but I'm the teacher. So 3B1 is a Hall effect. 1B1 is a Hall effect. 3B1 is a magnetic reed switch. Can you see how I can tell the difference? One of them is what? Yeah, one of them's 2 wires and there's 3. So the reed switch goes through, right? You understand? It don't have to be powered up. But 3, instead of being the power wire, goes to the load, which is different. This is anybody got those down yet? So what type of sensor is this? Right here. This is a solid state sensor. Potentiometer would be drawn as a potentiometer. This is an inductive sensor. This is so y'all had me looking at an ultrasonic sensor, and this right here is a photoelectric sensor. So we're looking at module 2. This is a photoelectric. Right. I don't know if it's diffused. I don't know if it's through the beam. I don't know. All I know it's a transmitter and receiver. Since this is the Amatro line, I know it's a through the beam. Why? Because that's the only photoelectric sensor they have on the plane. No. Let me go back. All you're looking for is an LED with lights, with arrows in it. Magnet read. I was looking for this guy doesn't have a capacitive. I'll bring up the next module and make sure you know the capacitive sensor. We're okay here now, right? Everybody okay there? So this is a what? That's the light, right? Inside the push button. This is the solenoids. They're drawn wrong. They're drawn because they left off the slash. The guy who ever drew it left off the slash. And this is the actual what? Valve. This is why you can see he's got it drawn wrong. Because the ISO symbol, so in motor controls, we say a relay coil is round. The ISO symbol for a relay coil is this triangle, this rectangle right. Now I know it's a relay coil because it's labeled K. K means relay. It's the coil of the relay. And this is standard. K, you see that used all over. So you can see why you would kind of get confused here because this is not a relay, this is a solenoid, even though they operate basically the same, right? You understand? They're both coils of wire, but one of them moves an actuator. The other one controls contacts. So this one right here should have that slash line through it. So Gert, when he drew this one, he didn't draw it quite right. So this doesn't draw the motor. Now, most control circuits, so what makes up when we talk about a control circuit, what makes up a control circuit? Have we talked about that in the class? If we didn't, we need to. Close. So this is the basic control system. Now if we come back over here and do something like this, this is what we call feedback. And this would be called a closed loop system. Also referred to as a servo system. So we had one of our guys, I don't know if y'all know Joe Bear, Preston. Joe Bear went to 3 interviews lately. And he said just about every question that they asked him, they had gone over in our class. So the guy asked him what was a servo motor. A servo motor is a motor that provides feedback. So it's built into the motor. So this is a closed loop system. So what do we mean by feedback? Feedback means I tell my actuators what to do, and then I verify that it's been done. Now what's this gonna come from? Sensor. That's right. That's exactly it. So just about everything we have over there is closed loop. Not everything. So we can watch that robot go over there, and I don't have any pistons over there, and the robot just goes over there and goes down and clamps it down. So there's no feedback in that system. So the problem with feedback is the system becomes more expensive, right? So there's going to be some things at your factory that are open. If they can get by using open loop, they're going to use open loop because why? Cheaper. If they can't get by with open loop, then they'll use closed loop. Because now my controller's got to be more precise, right? You understand that? So yeah, y'all can watch that robot over there on the Festo line. If we don't have a piston over there in the back, the robot will swing over there, it'll go down, and close its hand. But that robot over here don't know there's a spring there. So if you don't go out there and move the spring out, it does what? You reset it, it'll go up there and do what? Grab one, come over and do what? Set it down right on the top of it. So that's what? That system there is open loop between the robot controller and that right there. Now, normally what we have in the control system is we have what we call a control section. And then we have what we refer to as a power section. So your power section might be in here, right? You understand? So this is what's nice about relays. So I can come over here and I can have a relay that runs off of 24 volts DC. But the contacts it controls might be controlling 2000 volts AC. So what's nice about a relay is that you can change the type of voltage that you use. So your coil might be rated as DC, but your contacts might control an AC system. This guy right here might be rated at 20 milliamps. This motor that I got over here might require 300 amps. Well, what we would do is we would go between our PLC, would bring in the relay, and then the relay can run the motor, right? You understand what we're saying? So PLCs does not, this is where your PLC goes right there. Your PLC is your control section. Your power section, this is where your motors are going to be at, the big actuators and all this other kind of stuff that you're trying to run. So the PLC could bring in a what? A relay. The relay's in the control section, but the contacts could be controlling stuff in the what? In the power section of the system. You understand that? So PLCs do not do away with relays, because a PLC cannot run a 200 horsepower motor. But a PLC could pull in a relay, and the relay could run the what? 200 horsepower motor. So all your motors and big stuff like that, that's over in the power section. Then your PLC's controlling that usually through a relay, right? That makes sense. So like this PLC can't run that motor over there, but what can we do? So all we show on the PLC diagram, all we show is this relay coil right over here. Because this is the electrical part of the control system, they don't show what? They don't show the contacts on the motor. And it basically, they do on the Festo line, which is really, really neat. And we will talk about motors too, by the way, so we need to have a basic understanding of motors. Anybody know how we control the direction of a DC motor? We change the polarity. We change the polarity on the rotating part. We call it the armature. And we usually do it with what we refer to as an H control. So that's the symbol of the armature or the rotor of a DC motor. And this right here would be plus, this right here would be minus. So if this one's forward, this would be forward, and this would be the contacts controlled by the reverse, and this would be the contacts controlled by the reverse. And where's the relay at? Well, the relay's over in the control section, right? Understand? So what happens if I come over here and close forward, then the current flow would be up. It's going to go through the motor in that direction. It's going to come up and go back through here. So we got to make sure that the forward and reverse are never energized at the same time. Because if forward and reverse energized at the same time, I'm going to be connected negative to positive when we have what's referred to as a short circuit. So we'll go over there in a minute and show you how they prevent that. Of course, it's up to you as a programmer to make sure you don't do that, right? And of course, if we do it, if we're going to run it in the reverse direction, I close this one and this one. Now the current flow is going to be up, and it's going to go what? In that direction back to there. So it takes two relays. One's forward, one's reverse.